Hi, folks. I hope y'all had a fantastic weekend. We are starting the day 14 material, which is proof by cases. Let's go ahead and get started. Before I get started, let me remind you that there is a Canvas quiz that is due this week and a written homework that is due early next week, Sunday night. So don't put those off too long. Okay? A proof by cases is a verbal implementation of the following argument. That we know that either P or Q is true. We don't know which one, but one of these is true. Maybe both. But we know that P implies R, and we know that Q also implies R. And therefore, regardless of which one of these is true, one of them will imply R, and therefore R has to be true. That's the idea of a proof by cases. Okay? We can, in fact, extend this to multiple OR statements as long as everything that we have split up, all of the cases imply R. Okay? This is just a proof by two cases argument, but we can do proof by any number of cases. All right. Proof is a good option for trying to prove results that involve even and odd parity, where we have to look at two cases. What if this is even? What if this is odd? And if they both lead to the same result, then we've completed our proof. Results involving sign, where the sign could either be positive or negative. We just look at both possibilities and see what happens. Or events that have a small outcome set. A coin could be either heads or tails, and if both of them lead to the same result, then we can use a proof by cases for that. Or a roll of a die, or something where we are looking at something where we may not know in advance what the outcome is going to be, but we know that the number of outcomes is small enough that we can check them each individually. Okay? So let's try some examples. We're going to try to prove for all integers that n squared minus n plus 3 is odd. Okay? So we're going to start with let n be an integer. Now, if I knew that n was even, I could set n equals to 2k and then show that 2k squared minus 2k plus 3. I could rewrite using, factor in a form of 2 times some integer plus 1, use the closure axiom and show that was odd. And if I knew that n was odd, I could do that same thing, but start with 2k plus 1. But if I just have an integer, I don't know how to factor this into 2 times something, because I don't have any 2's to factor out here. And so what we're going to do is we're going to look at the two cases. So we're going to let the reader know that we are looking at two different cases. So we consider two cases. And then we'll label them case 1 and case 2. In the first case, we're going to assume n is even. Then, now we're going to just do a direct proof of just the even case. Then there is an integer k. Such that n equals 2k. Then n squared minus n plus 3 is equal to 2k squared minus 2k plus 3 is equal to 4k squared minus 2k plus 2 plus 1. I'm splitting up that 3, so I can go ahead and factor this now. 2 times 2k squared minus k plus 1 plus 1. By the closure axiom, (2k squared minus k plus 1 is an integer, and so n squared minus n plus 3 is odd. This is a typical direct proof, but it only works if n is even, because I replaced n with a 2k. So now we're going to look at what happens if n is odd, and see if we can get something that works out the same way. Assume n is odd. Then there is an integer. All right. I've used k up here. Interestingly, I'm allowed to go ahead and use k again down here because these can't happen simultaneously. There is no universe in which n is odd and even at the same time, and therefore if n is odd, this k never got defined, and so I'm not defining k to be two different things. That's the thing that we're usually not allowed to do. We're not allowed to define a variable to mean two different things. But if n is odd, this k never got defined. And so I'm free to continue to use k down here. But if I don't want to use k, if I'm not sure that it's safe to use k, and I'd rather use a different letter of the alphabet, that's okay also. Okay? So let me make a comment here in red. That is, we may use k here. It is not being redefined. But it's okay to use a new letter. Okay? So if you're not sure whether you're redefining a variable or not, then just pick a new letter and you're safe. Okay? But we can use a k here, such that, let's go ahead and change the pen size again. N equals 2k plus 1. All right, then n squared minus n plus 3 is equal to 2k plus 1 squared minus 2k plus, minus 2k plus 1 plus 3. And that equals to 4k squared plus 4k plus 1 minus 2k minus 1 plus 2 plus 1. Again, I'm taking this 3 and splitting it into 2 plus 1. I see this 1 and the minus 1 cancel, and 4k and 2k combine. And so we get 2 times 2k squared plus k plus 1 plus 1. Okay? Up here we got minus k. Down here we're getting plus k. And that's okay. These are two different cases, but by closure, this is also an integer. By the closure axiom, (2k squared plus k plus 1 is an integer. And so n squared minus n plus 3 is odd. All right. So this is a proof by cases. We consider two cases. We look at the case, what happens if it is even, and we come up to a result that n squared minus 3 is odd. And we look at the case where n is odd, and we show that n squared minus n plus 3 is also odd. And so it didn't matter whether n was even or odd, and so this is true for all integers. But we had to break this up into two parts and prove the two parts separately to get the result that we wanted. Okay? So let's try another example. Prove for all integers if n is not divisible by 3, that n squared is not divisible by 3. So if a number is not divisible by 3, so if n is not divisible by 3, well, that means we can't write it in the form 3 times k. This is just thinking right now. This is not my proof. This is my thought process. Excuse me. If n is not divisible by 3, then n doesn't equal to 3k. That means that when I divide 3 goes into n, that there's going to be some number left over, and that remainder has to be either a 1 or a 2. And so n will be 3k plus 1, or n will be 3k plus 2. It'll be a multiple of 3 with 1 left over, or a multiple of 3 with 2 left over, and you can't see that, so let me write this over here. But we don't know how much is left over, if it's 1 left over or 2 left over. We just know it's not divisible by 3. So we look at these two cases separately. Okay? So let n be an integer. Which is not divisible by 3. We consider two cases. The first case is we're going to assume there is an integer k such that n equals 3k plus 1. And for the second case, we're going to assume there is an integer, integer k such that n equals 3k plus 2. So that's my two cases. It's not divisible by 3, which means there's got to be a remainder. We just don't know what that remainder is. So we look at both cases and see what happens. So in this first case, we'll do the calculation. Then n squared is equal to 3k plus 1 squared, which is equal to 9k squared plus 6k plus 1, which is equal to 3 times 3k squared plus 2k, close parentheses, plus 1. By the closure axiom, (3k squared plus 2k) is an integer, and so n squared will be 3 times an integer plus 1 left over. So n squared is 3 times an integer plus 1 left over. And so n squared is not divisible by 3. Okay? Well, then let's see what happens in this case. Assume there's an integer such that n is equal to 3k plus 2. Well, then n squared is 3k plus 2 squared, which is 9k squared plus 6k plus 4. And that's 3 times 3k squared plus 2k plus 1 plus 1. All right. 3 times 1 plus 1 gives me 4. There's where that 4 goes. By the closure axiom. (3k squared plus 2k plus 1 is an integer. So n squared is 3 times an integer plus 1 left over. And so n squared is not divisible by 3. All right. So in both cases, we were able to get to the result that n squared was not divisible by 3. In both cases, n squared was a multiple of 3 with 1 left over. Okay? All right. Let's try another one. Prove that if n is any odd integer, then n squared minus 1 is divisible by 8. So this is going to be a little tricky. How are we going to get to be divisible by 8 if all we know is that n is an odd integer? Okay? So let me show you where the tricky part comes from. If we just launched into this is, again, just a thought process, not the proof. N is an odd integer. That tells me that n is 2k plus 1 for some integer k. Well, then n squared minus 1 would be 2k plus 1 squared minus 1, which is 4k squared plus 4k plus 1 minus 1, which is 4k squared plus 4k, or 4 times k squared plus k. Well, that 4 tells me it's a multiple of 4, but we need it to be multiple of 8. So this is a multiple of 4. Well, the multiples of 4 came around because I was taking this 2 and squaring it. So if I did 4 and squared it, I'd get a 16 somewhere. I might be able to do this if I knew, if I could put n in the form 4k plus something instead of 2k plus something. But if an n is an odd integer, and I divide an odd number by 4, it could be 4k plus 1 left over, or it could be 4k with 3 left over. When I take an odd number and divide it by 4, I have both possibilities for the remainder. And so I have two cases I'd have to check if I want to use, instead of a 2, I want to use a 4 here, so that I can maybe get a bigger coefficient. So let's see what happens. Let n be an odd integer. We consider two cases. Case 1, we're going to assume that n is equal to, let's say, assume there's an integer k, such that n equals 4k plus 1. And the other case is going to be assume there is an integer k such that n equals 4k plus 3. And then we work out the details then. Then n squared minus 1 is equal to 4k plus 1 squared minus 1, which is equal to 16k squared plus 8k plus 1 minus 1, which is equal to 8 times 2k squared plus k. By the closure axiom, k squared plus k is an integer. And so we have 8 times an integer. So n squared minus 1 is divisible by 8. So if we try this with 4k plus 3, then n squared minus 1 is 4k plus 3 squared, which is 16k squared plus 8k plus 9 minus 1, instead of 1 minus 1. But that's okay, because 9 minus 1 is 8. So that's 8 times 2k squared plus k plus 1. We have a plus 1 here that we didn't have up here. But that's okay. By the closure axiom, two k squared plus k plus 1 is an integer. And so n squared minus 1 is divisible by 8. All right. Proof by cases works because we couldn't have proven this easily for all odd integers at once, but we could split the odd integers into two types and show it for each of the two types separately. Okay? All right. Proof if a is not equal to 0, then this determinant is negative. Okay? All right. So let's suppose a doesn't equal 0. Well, we can then consider two cases. Case 1, assume a is positive. In case 2, we're going to assume a is negative. Okay. Well, then the determinant of A, or the determinant of the matrix, will be A times negative A minus A squared. This will be a positive term, and this will be a negative term. And A squared will be minus a positive term. Since A times negative A is less than 0, and A squared is greater than 0, A times A negative A minus A squared will be less than 0. And so the determinant is negative. Now, the other case is really very similar than the determinant. A negative A. Instead of this being positive times negative, this was now just negative times positive minus positive. And so since A times negative A is less than 0, and A squared is greater than 0, A times negative A minus A squared is less than 0. And so the determinant of A negative A is negative. All right. So I want to talk a little bit about this example. It's different from the last two that we've done. So I want to back up to the last two examples. Go to example 2, and I'll use a color to highlight this. Along the way, when we were doing the calculations for case 1 and case 2, we got different results. Here we got a +1, here we got a +4. And therefore, we didn't get a +1 inside the parentheses, and we did here. That the calculations for these two cases, even though the thought process was very similar, the calculations worked out differently. In example 3, the calculations worked out differently. This was a +1, but this was a +9. And so we didn't get a +1 in parentheses here, but we did get a +1 in parentheses here. And so even though the thought process was very much the same in both cases, the calculations turned out to be different. But in this example, I was multiplying a positive times a negative here, and I'm multiplying a negative times a positive here, and these turned out to be exactly the same. And this turned out to be exactly the same. And so if the proofs of the two cases turn out to be the same, is there a shortcut that we can use? And there is, and we have to be a little careful about using it, because the shortcut is not allowed to, we're not allowed to use the shortcut to skip over a step in a proof. It's a step to show that the proof actually works out to be exactly identical logic to the proof of another case. We use the phrase without loss of generality to indicate that the proof of one case has exactly identical logic to the proof of another case. And the only difference between the proofs is a typographical nature, like changing the order of two terms, or changing the names of a variable from y to x or from n to k or something like that, where it's a typographical difference, but it's not a logic difference. And we could have used this shortcut on example 4, but we didn't. But on the next example, we'll use the shortcut, and I'll show you how it works, okay? So here's the next example. Example 5 proves that if A and B have opposite parity, that is, one is odd and one is even, then their sum is odd. Okay? So I should have put in here, let's prove that if A and B are integers that have opposite parity. Things that aren't integers don't have a parity, but that's, I would like to be careful here. So the proof would begin with let A and B be integers with opposite parities. So let A and B be integers with opposite parity. Now we have two cases. The first case is that A is odd and B is even. And the other case is that A is even and B is odd. Okay? So if we didn't use the shortcut, we would then say we consider two cases. Case 1, assume, I'm going to leave some space here, A is odd and B is even. And let's go ahead and write out what case 1 does. Then there is an integer k such that A equals 2k plus 1, and an integer j such that b is equal to 2j. Then a plus b equals 2k plus 1 plus 2j, which is 2 times k plus j plus 1. By the closure axiom, k plus j is an integer. And so, therefore, A plus B is odd. Now the proof for case 2 would be exactly the same logic if I replaced all of the A's with B's and all of the B's with A's. That if A is even and B is odd, then B would be the 2k plus 1 and A would be the 2j. A plus B would still be this, would still equal this. This number would be the same. This number would be the same. The calculations work out exactly the same way in the other case. And so the logic is exactly the same in both cases. If I don't have a calculation difference at all in the cases, even just an extra, like a difference between a plus 1 and plus 9, I can't use the shortcut here. I have to show both calculations. But when the calculations turn out to be exactly the same, like in example 4, and like in this example here, then the shortcut is I don't have to say we are considering two cases. Instead, we're just going to do the one case. We're going to just cross all of that out. And we're going to say that this assumption can be made without what's called loss of generality. That is, this case is not so specific that it doesn't apply to this one. This case can be generalized to this case here. And so generalization is not lost. This is a weird phrase that we've sort of inherited, but this without loss of generality is a statement that says, I am really doing multiple cases here, but the multiple cases have the same logic. And I don't have to then tell that there are two cases. I'm just doing the one case without loss of generality. Let's do one more example involving a without loss of generality shortcut. And again, this is just a shortcut. If you're not sure whether you can use it or not, if you're not sure if it's safe to use, don't use it. It is perfectly okay to go ahead and write out both cases. But if you are looking for a way of saving yourself some time, if the logic is exactly the same in both cases, except for just rearranging some letters, typographical changes, you can say this without loss of generality. Okay? So here's another example we can use loss of generality. If r, s, and t are three consecutive integers, then r plus s plus t is divisible by 3. Now we're told that they're consecutive, but we don't know what order they're in. So these integers are consecutive, but the order could be RST, but it could be RTS, or SRT, or STR, or TRS, or TSR. It doesn't say in the problem that these integers are given to us in order. We're just told that they're consecutive. But the proof for each of these 6 different cases is going to be the same proof with just changing the letters around. So let's look at a proof for one of the cases. So we're going to start out by saying let R, S, and T be consecutive integers. I'm not going to say we are considering 6 cases. I'm not going to say that. And I'm not going to label the first case, case 1, because it's going to be my only case. I'm going to leave those 2 things out. And instead, I'm going to go straight to saying assume. And here's my weird phrase that indicates that this one case is going to do the work for all 6 without loss of generality. That's my phrase that says I am writing one of the cases that if these are consecutive integers, that s is equal to r plus 1 and t is equal to r plus 2. And now let's do the calculations. Then r plus s plus t is equal to r plus 1 plus r plus 2, which is equal to 3r plus 3, which is equal to 3 times parentheses r plus 1. And then by the closure axiom, r plus 1 is an integer, And so r plus s plus t is divisible by 3. That's the proof for the case where the integers are in this order. And if I want to write the proof for any of these other 6 cases, I just have to move the letters around, but the calculations won't change. If s is the smallest and it goes s and then t then r, this will be s plus 1, s plus 2, 3s plus 3, 3s plus 1. S plus 1 is an integer, so s plus t plus r is divisible by 3. And we could do it that way also. That is, the logic didn't change, I just have to change all the r's to s's and do the problem that way. All right? So that's how proof by cases works. We are looking at a problem that we can't tackle all at once, and so we separate it into pieces that we can solve. We solve each of those pieces, and if the solving of those pieces turns out to be identical except for typographical changes, then we can use this shortcut that says loss of generality. But if there's even, a sign difference or a constant difference, or if there's any kind of change at all in the calculations and the logic of the proof, we have to show each of those cases separately. Okay? All right. Take care. I'll see you guys Wednesday.